Hey folks, welcome back. Let me adjust the camera so you can see me. There we go. We started talking yesterday about partial fractions. I'm going to continue that discussion today. Hopefully you had a go at a few initial practice problems from those partial fractions that I suggested and have started maybe working on the web work. Today we're going to extend the ideas that we had in yesterday's lesson. So here's the kind of problem we were looking at yesterday. We had an integral which was a proper rational function. So polynomial over a polynomial. Here I've got a third degree on the bottom, a third degree on top, fourth degree in the denominator. So it's proper. And you can see the denominator is factored. And the idea here is to rewrite this integrand, everything that I want to integrate there, rewrite it as just the sum of the linear factors. So if I've got the four linear factors in this case, I'm going to have four constants, a, b, c, and d, and we're going to end up having to find those four constants, a, b, c, and d. And then the integral is just going to be the integral of that quantity, where our whole job essentially, because the integrals here are each very hopefully easy to do, our goal here is to find the a, b, c, and d. And that's what we talked about yesterday. But what this relies on is that these four linear factors, the x minus 2, the x plus 1, the x plus 2, they're all different. Right? This is an x minus a different number each time. We've got no repeated factors. Today we're going to start by looking at what happens when we've got repeated factors. And here's the general rule. Essentially, we take every possible power of that factor that's in the denominator. So you see in this case, we have, let me go to yellow, we have three different terms down there, but it's a fourth degree polynomial because this one's repeated. So this factor, x minus 2, has multiplicity 2, which is just the name for that power. Everything else here has multiplicity 1 because it only appears once. Well, what this rule says is if you have a repeated linear factor, then you take every power up to the power that you see of that linear factor. So in this case, we see x minus 2 raised to the power of 2. So what we're going to do is take that term that we're going to integrate and we're going to look at each factor one by one. In fact, let's start with the easy factors. Let's start with the factors we had last time. Last time we said if I have a distinct linear factor, then I just get a constant over it. So a over x plus 1, let's say, and b over x minus 3, because I have those two linear factors. They only appear once, so they're not repeated, they're distinct, and they each contribute a term. But our new rule says if you have a repeated linear factor, x minus 2, in this case which is squared, then I need to add that x minus 2 to every power to which it appears, and then with a constant on top. So for every power up to the value that it appears. So we've got x minus 2 squared, so I need every power of x minus 2 from 1, 2, 3, all the way up to, well, 2 in this case. So it's just the first two terms. If this was a fifth power, then this would be 1, 2, 3, 4, and 5. So you need every single term that it appears. And then we do the same thing. We rewrite this whole thing back in terms of a common denominator. And now things are going to get more complicated. Because if you think about the common denominator here, this first term, I'm going to have to multiply it by everything that's missing. So there's already, think about it this way, there's already an x plus 1 in the denominator here, which means I need to multiply top and bottom by two x minus 2's and an x minus 3. So I'm going to get an a times x minus 2 twice, and then an x minus 3, and then I'm going to put all of that under the same denominator we had before. The second one, well, the b's already got the x minus 3. What's missing? Well, what's missing is the x minus 2 all squared and the x plus 1. Think about each of these terms. The x minus 2 here cancels, the x minus 3 cancels, you're left with a over x plus 1. For the b term, the x minus 2 cancels with this one, the square of it. The x plus 1 cancels, you're left with b over x minus 3. That's what this is. And then the last one, well, not the last one, the c term, it has a power of 1 here. So what's it missing? Well, it's missing one of the x minus 2's and then the other two terms. So this is going to be an x minus 2, x plus 1, x minus 3. Don't mind me while I create more room. I just move that across. Because we've got a last term, the last term is the d, it's already got x minus 2 in the denominator twice, so it's just missing the other two terms. It's missing the x plus 1 and x minus 3. And if you go through that term by term and cancel things down, you should see that it reduces back to this. And you need to be able to convince yourself that you know why I ended up with this. So it's kind of complicated looking. But what we've got is the numerator here and the numerator here look different, but they're equal. The denominators are the same, so those numerators must actually be equal. So I'm going to grab those two things and go to the next page. So what we've got here is our second example. So here is the numerator from the previous expression. Let's go back. We're looking at 4x squared plus 2x minus 1 is equal all of this stuff in the numerator here. I've just rewritten that expression here. And the goal here is to solve these equations for a, b, c, and d. It has to be true for all values of x. It looks daunting, but an important idea to remember is if we choose smart values for x, then we can simplify that equation. So one smart value for x, for example, is x equals 3. So if I were to choose x equals 3, that's probably a bad color, but if I were to choose x equals 3, then I can say, I can drop half of the terms. Because when x equals 3, well, I'm going to get 4 lots of 3 squared plus 2 lots of 3, you get the idea, minus 1 is equal to, plugging 3 into this first term gives 0 because of that term. Plugging 3 in here gives 0 because of this term. Plugging 3 into the last one gives 0 because of that term. So the only thing that's left, actually, is the term, I think, that involves the b. So we'll have b, 3 minus 2. What do we get? We get the b is 41 over 4. Hopefully, if you check the algebra there, you'll see that I'm right. And if I'm not right, let me know. When x is minus 1, this term drops out, and this term drops out, and this term drops out. So we're only left with the first term. So 4 lots of minus 1 all squared plus 2 lots of minus 1 is equal to, the only term that's going to be left is the a term, and we're going to have minus 1 minus 2 all squared, and then we're going to have minus 1 minus 3. And so that's going to give us something like that. 1 is equal to, I think, if that's right, 3 squared is 9 times negative 4 is minus 36a. Close enough. The point here is that it's going to be some number. And in this case, we've got a number. So the other thing to plug in is x equals, the other obvious thing to plug in is x equals, what haven't we done? X equals 2. This is the term that doubles up, and this is going to lead to a slight complication, because when I plug in x equals 2, the first term drops out, the second term drops out, the third term drops out. All I've got left is the fourth term, which I think gives us 19 equals minus 3d. Excuse my bad d's and b's and things. So that's minus 19 over 3. That's our d value, if I got that right. But I can't plug in 2 again to find c. So we can find a, b, and d very easily, and then we need to find c. The easiest way to do that is usually just pick a small number like 0 that simplifies things as simple as possible, because the fact that it doubles up means that I can't plug in a nice number to find c. It's not going to be so straightforward. But if I plug in x equals 0, then on the left I just get the minus 1, and on the right what we're left with is something more complicated. And so we have a complicated expression here that has a's and b's and c's and d's in it. And so we need to plug in and solve for c, because we know a, b, and c, and d. So our job's just to solve for c. And when I do that, I found that c is minus 464 over 27. Sorry, positive. Okay, and that's a calculation you just got to sit down and do. Plug in the a, b's, and c's. If you've got a calculator, it's not too bad. If it's on a test, it's going to be a simpler calculation than this. I'm not going to give you something so messy to work with on a test. But the point is, we've now got the a, b, c, and d. And that's exactly what we were looking for this whole time, because we wanted to rewrite this expression. This is the integrand. This is the thing we're going to integrate. We wanted to rewrite it in terms of those factors. Well, we found a. We found a was minus 1 over 36. And we found b. We found b was 41 over 4. And we found c. It was ugly. It was 464 over 27. Notice that these aren't going to change the integral that we do. And the last one is d, which is minus 19 over 3. And that lets us write down the partial fraction decomposition. And solving that, and so that equation is not pretty, but we can plug in for the a, b, and d because we have them. And solving that leaves us minus 92 over 9. Now, if I give you this on a test, you'll have nicer numbers here. This will work out more simply. But in principle, we can do it. You can plug in a, b, and d and solve this for c, because you know everything except for that one value. And there's nothing special about 0. The idea is it simplifies things, but maybe x equals 1 would have given us easier values. Any value will work here. Okay, and that gives us what we want, because our entire goal was to take this term, this thing we wanted to integrate, the integrand, and write it as partial fractions like this. So we need to write it using a, b, c, and d. And we know a, b, c, and d. We can just simply go back and replace them. And so there you go. I've replaced a, b, and c, and d with the values that we just found. And now this is completely integratable. These first 4 rule that we can integrate, right? This is u to the minus 2. And so integrating that, we get minus u to the minus 1, if you like, plus a constant, which is 1 over u. And what was u? U was x minus 2. So it's negative that plus a constant. And that's what I did. I just wrote it that way. The 19 over 3 was a negative to begin with, so we got a positive there. So this is how the integration behaves. If I'd started with a term that had like a 5 there, then imagine what we'd get. We'd get this kind of thing with a bunch of constants, and we get a power of 2 and a 3 and a 4 and a 5, and then we integrate them. They'd behave very much like this one did, and so we'd end up with a power of 1, a negative 1 here, and the power of like this, and then a power of negative 2 when I integrated 1 over u cubed, and so on. So there's going to be some web work questions like that. Have a go at some follow-ups from that question. I'm going to do another example or two where I look more at the factoring of this, and then tomorrow I'm going to look at factoring irreducible quadratics. So sometimes you can't completely reduce something to linear terms using real numbers, right? If you imagine a quantity like x squared plus 1, I can't factor that any further in terms of real numbers. There is no linear, I can't factor that into 2 linear factors. So there's one case where we can't really deal with yet, and I'm going to look at that tomorrow. But let's explore what we've seen so far a little more today. The first thing to notice here is that the degree of the numerator and the denominator are both 4. In other words, this is not a proper rational function. This is an improper rational function. So our first job is to make it a proper rational function, because everything we've talked about applies to proper rational functions. And so to do that, we're going to have to do the long division. And this is where the synthetic division, you may know, won't help you, because we've got to long divide polynomials where the thing in the denominator is not just linear. So let's do that long division. Okay, it goes inside the denominator, or inside this division sign. And notice that if there's a missing term, so this has no x cubed term, make sure you put that 0 in there. In fact, this should be 0x cubed. That's the important thing. If there's a missing term, make sure you include that in the thing when you write it down, because otherwise you'll mess things up. All right, so now I want to know how many x's to the 4. I'm writing a number here, and the number I write here is going to multiply this whole thing, and I'm going to write it in the line below. Remember how this long division stuff works? So I'm going to multiply this 1 by x to the 4. And the reason I chose 1 is because I want these two to be exactly the same so I can cancel them. Because the next line is this minus this is 0. Right? And I want to cancel the leading terms. So I'm asking, what multiple of this do I need to produce this? What multiple of x to the 4 do I need to produce x to the 4? And the answer is 1. So when I multiply that out, I've got to multiply every term. So I get 5x cubed. 8x squared, I'm multiplying everything by x, by 1, remember, minus 4x plus 0. So I'm just taking this 1, multiplying it through that whole thing, writing it here, and then I subtract them. At the risk of being overcolored here, I'm subtracting all of that. So the x to the 4 in yellow minus the x to the 4 in blue, that's 0. The 0x cubed minus negative 5x cubed leaves us 5x cubed. It's a positive. 1x squared minus 8 of them leaves us negative 7 of them. Minus 2, subtract minus 4, well, that's the same as adding 4. 4 minus 0, well, that's 4. And so we have the remainder, if you like. And so we can now rewrite this expression. We can rewrite this original term up here. We can rewrite this whole integral that we had before, just this rational function. Well, the quotient was 1. So the remainder here, it's 1, this original fraction, what I'm saying is this original fraction is 1 plus this remainder, right? So I'm literally saying this is the remainder out of the thing I divided by, and there's the thing I divided by. So we'll put that in the denominator, and there we go. And there's our expression for this ratio. So all I've done is rewrite this ratio as 1, that's the quotient, plus the remainder over the thing I divided by. And I'm doing the integral, so I'm taking this whole integral. And now this is easy. I know how to integrate 1 with respect to x. And so now what we've got to do is apply the ideas we've had in the last couple of examples to solving this problem. And it's similar to the one we looked at last, but what's different now is I haven't got it fully factored. The denominator is a cubic, but it's not fully factored. And I'm just going to drop that 0 at the end there because that's just a 0, right? There's really nothing there. So this is the term we're working with. And so our job, as it has been the whole time, is to factor that denominator. And then we match that numerator with the partial fraction decomposition we come up with. Big picture, right? When you're looking at this, look at the big picture. Because there's lots of calculations going on in these problems. Ask the big picture, because that'll help you solve them. Is it a proper fraction? If it is, go to right where we are now and just start doing what we're about to do. But if it's not a proper fraction, do a division and make it a proper fraction. All right, so let's now work on this sort of sub-problem. Again, now we've made it an integral that we can do using our techniques because this is a proper partial fraction. Our job is to take that denominator and factor it, and then build partial fractions. And notice that the denominator is easy to factor at least the first time because I can factor out an x because there's a nice common x there. I mean, factoring is hard. Here's one way to approach it. So I can factor out an x and I end up with that, right? And so this is, I'm going to give it a name just so that I don't have to write all of that every time. I'm going to call it x times q of x, right? So we've got the factor of x in the denominator. What's happening with q? Everything that's left here is what I'm calling q, just so I don't have to rewrite it. Okay, so notice, and this is a trick that can be helpful. I know this because I built the problem. Notice that q of 1 is equal to 0. It's 1 cubed minus 5 plus 8 minus 4. That's 9 minus 9. That's 0. So this is something I noted before. What we know is that x minus 1 is a 0. This follows directly from the properties of polynomials. If the function's equal to 0 at the point, then x minus that point is equal to a factor. In other words, x minus 1 is a factor of the polynomial. So I've got a cubic here, and I know one of its zeros. I know that 1 is a 0, which means x minus 1 is a factor, which means we can do a division. So we're going to take the q, and we're going to divide out the x minus 1, and see what's left. So again, we go through and we say, well, what do I need to multiply x by to get x cubed? Because this has to be an x cubed, right? And then I'm going to squared x cubed. X squared times x is x cubed. X squared times minus 1 is minus x squared. And that's it, right? Multiply the x squared by all of this, write it down, cancel. So when I do that cancelling, in other words, I'm subtracting those terms from above, what I'm left with is no x cubes, and minus 5 plus 1, so minus 4x squared plus. And I'm just going to drop the other two terms down because they're not playing the game, essentially subtracting 0 from those two. I'm just dropping them down. And then I look at the next term and I say, well, I've got an x. I want negative 4x squared, so I need to multiply by negative 4x. Doing that gives me negative 4x squared. Taking that negative 4x, multiplying it by x, taking that negative 4x, multiplying it by minus 1, leaves us plus 4x there. Cancelling those again. These cancel. I've got 8 minus 4. That leaves 4x minus 4, just dropping that down again. And then looking at, I've got 4 times x minus 4. I want to multiply this then by 4 because that produces 4x minus 4. And when we've done that, we get 0 at the end. It has to be 0. This is the remainder, remember? And the remainder must be 0 precisely because I claimed this was a factor. If it's a factor, the remainder is 0. There's the remainder. This is all properties of quadratics that hopefully you remember. So what we've shown here is that q of x itself can be factored into the factor x minus 1, and then this piece. And this piece is x squared minus 4x minus 4, and then plus 0, but I don't care about the 0. But the whole denominator had an extra x in it, so the whole denominator is x q of x. So here's the whole denominator. I'm almost done, right? I can factor that last term. That last term is a quadratic. Hopefully you can see maybe that the factor here is Oh, I don't know, what's the factor here? Well, it's a lot easier if I don't make a transcription error. That's a positive. So this is x minus 2 all squared. Because you square that out, you get x squared minus 4x plus 4. So there's our complete factorization of the denominator. So now we go back to this integral and we do the partial fraction decomposition. Again, next page. So in this case, you can see what we've been able to do. On the last page, we simply factored the denominator. Now we need to do a partial fraction decomposition, right? I'm not dealing with the integral at all. I'm just writing at the top to remind us what we're doing. What I'm dealing with is all of this stuff, and I'm going to now do some work on it. I lost the dividing line. There we go. So we're now working with this partial fraction, right? We want to write that as a partial fraction. And just looking at this form immediately tells us that we should use a over x, b over x minus 1, and c over x minus 2. But that term was squared, so there's going to be a d over x minus 2 all squared. Okay? And then we put it back over a common denominator. We put it back over a common denominator where we've got the x minus 1, and then the x minus 2 all squared up down in the denominator. But then we need to combine everything else. And let me just write that out. And just like before, our goal here is just to put in the things that are missing, essentially. There's an x in the denominator here. I put in the other terms, x minus 1, x minus 2 squared. Because what I'm thinking is that all of that's going to cancel with all of that, and what we're left with is just a over x. And then the same argument for b and c. And that leaves us with these terms. And our job now is just to compare the numerators and use that to find a, b, c, and d. All right, so just equating the numerators here. For all values of x, we need this to be true. The numerator here is equal to the numerator here. And we can choose some simple values to make progress. So just like before, we could choose x equals 0. And if we choose x equals 0 in the first equation, all the last three terms drop out here, and we're left with, I think that's minus 4a. So that tells us a is minus 1. And then another easy one we can choose is x equals 1. When x equals 1, we literally get 4 equals b, so we're done with that one. When x equals 2, again, this is the one that's not going to go so well with us, but when x equals 2, we get a lot of cancellation. On the left-hand side, we get 20, and then we're left with, I think, plugging x equals 2 in here gives us, 2d. So we're left with 20 is equal to 2d, so d is equal to 10. The last one, well, we've got to choose another value. And previously I used x equals 0 because, that was easy. But we've already used x equals 0. We're not going to get new information. I've already used x equals 1. That's an easy one. Small values, hope for the best kind of thing. So I'm going to try x equals minus 1. You can use any value of x. We need to know 4 things. We need to know a, b, c, and d. And we don't have enough yet. We know a, b, and d. We don't know c yet. So I need to pick some other value. So pick any value. It doesn't really matter. But when you choose x equals minus 1, I think what you end up with is minus 10 on the left. And then on the right, you're going to get something complicated that involves a's and b's and c's, which I think you get that. I just did it quickly in my head. But if you then plug in these relatively simple numbers, minus 1, 4, and 10 for a, b, and d, then you can solve for c, and the c turns out to be 2. So we have what we need. So let's put it all together. So putting this all together, here's the integral we started with. Remember, the first thing we did was a long division, and that brought out this leading 1, basically because we've got x to the 4 on the top and we've got x to the 4 on the bottom, so we've got one lot of the thing in the denominator. And then we factored the thing in the denominator. The numerator here wasn't used at all, right? We pretty much ignored that until the last step. But it comes in when we decide what the a, b, c, and d are. Because once we factored this, we get a term, a over x, and we found that a was minus 1. And we had a b of 4, and a c of 2, and a d of 10. And so just plugging those values in that we calculated on the last slide. And now we can do the integral. So the total integral here, after all of this work, is going to be reasonably straightforward, because this is very much like the problem we saw last time. Right? And here is our final answer. You can actually use the log laws to simplify it maybe a little bit, because I've got looking at these three, I can kind of combine them because I can take the 4 here. I can treat the -1 as a power, but I can take the 4 up as a power. I can take the 2 up as a power. So I could write this total thing as x minus the natural log of, well, on the top I'm going to get an x minus 1, it's the power of 4. I'm going to get an x minus 2. These are even powers, so the absolute value is not doing anything anyway. And then I'm dividing by that x there, because I'm subtracting log of x, and then I've got the other terms. So I don't know whether that's any simpler, but you might see it written in the book that way, because I'm just using the log laws to move the powers up and then combine the different terms. All right, so this is a pretty complicated problem, but in this one problem,